In this video, we'll discuss some facts about linear independence. Let's remember the definition of linear independence. A set of vectors is linearly independent if the vector equation x1 times v1 plus x2 times v2 and so on equals 0 has only the trivial solution. So what does knowing that a set of vectors is linearly independent, or dependent, tell us about that set? Is a set with only one vector linearly independent? Well, the corresponding vector equation would be pretty boring. It would just have one coefficient times one vector equaling 0. So if v is the 0 vector itself, then the equation x times v equals 0 would have lots of non-trivial solutions. In fact, every value of x would be a solution. But if v is not the 0 vector, then the equation x times v equals 0 would only have the trivial solution where x is itself the scalar 0. So the set v, with only one vector v in it, is always linearly independent as long as v is not the 0 vector. Okay, so that seems pretty simple. What about sets with two vectors? So let's consider a set with specific examples. So we've got a set with two vectors v1 and v2. v1 is the vector 3, 1, and v2 is the vector 6, 2. Is this set linearly independent? Well, you might have noticed that v2 is 2 times the vector v1. 2 times the vector 3, 1 is the vector 6, 2. So since v2 is 2 times v1, we can write negative 2 times v1 plus 1 times v2 equaling 0. And that's not a trivial solution. x1 would equal negative 2, and x2 would equal positive 1, and that gives us a non-trivial solution to this vector equation. In fact, you might notice that there's lots of those solutions. We could have used positive 2 for x1 and negative 1 for x2, or we could have used positive 4 for x1 and negative 2 for x2, and so on. So there's, in fact, lots and lots of solutions. But all we need to come up with is one non-trivial solution to know that that set with two vectors in it is linearly dependent. So in fact, whenever v1 is a multiple of v2, or vice versa, the set v1, v2 will be linearly dependent. Okay, so what happens if neither vector is a multiple of the other? So let's consider another specific example. This time v1 will be the vector 3, 2, and v2 will be the vector 6, 2. Is this set linearly independent? This time, notice that v1 is not a multiple of v2, nor is v2 a multiple of v1. We could use row reducing to solve this problem, but we really want to think about what happens in general when we have a set of two vectors where the vectors are not multiples of each other. So let's suppose we had a solution to this vector equation. So we had specific numbers, x1 equals some number, let's call it c, and x2 equals some number, let's call it d, where x1 times v1 plus x2 times v2 equals the 0 vector. So that means we have c times v1 plus d times v2 equaling the 0 vector. Now notice that we're not saying whether or not this is a trivial or non-trivial solution, just that we have some solution, and we want to know what can we say about these numbers c and d. Well, if c is not 0, then we could subtract dv2 from both sides and divide both sides by c. That's what knowing that c is not 0 gets us. It lets us divide both sides by c. And that tells us that v1 would equal negative d over c times v2, which means that v1 would be a multiple of v2, specifically that number, minus d over c times v2. But we started off by saying that v1 is not a multiple of v2. So that can't happen. So c must be 0. Remember, what we just did was we said if c is not 0, we get a contradiction. If we assumed that c was not 0, we would end up that v1 was a multiple of v2, which we assumed wasn't the case. We can do the same thing to show that d also must be 0. We would just solve for the other vector and divide both sides by d. So that means that both c and d must be 0. So we started with an arbitrary solution. We didn't know anything about the solution to this vector equation, other than it was a solution. And we showed that it had to be the trivial solution. So we proved that when two vectors v1 and v2 are not multiples of each other, then the set with those two vectors in it must be linearly independent. And we also know that when v1 or v2 is a multiple of the other, then the set is linearly dependent. So this completely answers the question. If you have a set with two vectors in it, if one vector is a multiple of the other, then the set is linearly dependent. If not, then the set is linearly independent. Okay, so we know what to do with one vector. We know what the situation is with two vectors. What if we have more than two vectors? Well, we have a theorem that we can prove using the same techniques that we just talked about with two vectors. So this theorem is called the characterization of linearly dependent sets. So it says if you've got a set, which we'll call capital S, of 2 or more vectors, then that set is linearly dependent if and only if one or more of the vectors in that set S is a linear combination of the others. So again, think about what we had with 2 vectors. We said that the set was linearly dependent if one of the vectors was a multiple of the other. So if we have more than 2 vectors, we say that the set is linearly dependent if one of the vectors is a linear combination of the others. So it's just a generalization of the situation when we have 2 vectors. In fact, we can prove more. It turns out that if S is linearly dependent and the first vector is not the 0 vector, then one of the vectors in the set is a linear combination of the preceding vectors. Not just a linear combination of the other vectors, but specifically a linear combination of the ones that came before. So let's look at an example with 3 vectors just to understand what this says. So let's look at the set u, v, and w, where we've got these 3 vectors pictured here. Notice that the vector w, which is colored in blue here, is in the plane spanned by u and v. Another way to say that is that w is a linear combination of u and v. So in this case, the set u, v, and w is linearly dependent. Think about what that characterization theorem said. It said if one of the vectors in the set is a linear combination of the others, then the set is linearly dependent. Okay, what happens when we have a slightly different vector? So we've got the same u and the same v, but now we've got a different w. So what we can't say, it's not enough to say that since w is not in the span of u and v, clearly we can see from the picture that w is not in the plane spanned by u and v. But that's not enough for us to conclusively say that u, v, w, that set with 3 vectors, is linearly independent. We would have to know that none of the vectors in this set is a linear combination of any of the others. And all we know right now is that w is not a linear combination of u and v. So we have to somehow convince ourselves that none of the vectors in this set is a linear combination of the others. But remember that second part of the characterization theorem. It says we can check the vectors one by one, and all we have to do is make sure that none of the vectors is a linear combination of the ones that came before. Let's see how that saves us a lot of effort here. Let's start with the first vector in our set, u. Since it's the first vector, there are no previous vectors, so all we have to do is make sure that u is not the 0 vector, and we can clearly tell from our picture that u is not the 0 vector. The next vector in our set is v. Now there's only one previous vector, so to check that v is not a linear combination of the previous vectors, we just have to make sure that v is not a multiple of u. But if v were a multiple of u, it would be pointing in the same direction or the opposite direction as u is. And again, we can see from our picture that that's not happening. Finally, we have w, and so now the previous vectors are u and v, and so we have to make sure that w is not a linear combination of u and v. But we already said that. We can see from the picture that since w doesn't live in the plane spanned by u and v, that w is not a linear combination of u and v. And so we can conclude that this set with 3 vectors is a linearly independent set. Now in general, we're going to use our row reduction techniques to check whether or not the vectors are linearly independent. But this characterization theorem can be very useful for proving other fun facts about linear independence. Here's a handy technique that we can sometimes use to quickly identify a linearly dependent set. What happens if we have a set of p vectors in Rn where p is greater than n? Okay, so let's think about what that means. P is the number of vectors that we're talking about, and Rn is the dimension of space that we're living in. So for example, we might have 5 vectors that all live in R3. So the number of vectors is bigger than the dimension of the space that we're living in. So let's give these vectors names. We know that there are p of them, so we'll call them v1, v2, all the way up to vp, as we typically do. So remember the definition of linear dependence. This set is linearly dependent if and only if ax equals 0, that matrix equation, has a non-trivial solution, where A is the matrix whose columns are the v's that we just named. Well, clearly that matrix has p columns, 1 for each vector. But how many rows does it have? Well, remember that these vectors live in Rn. So these vectors have n entries, and that means that our matrix has n rows. So A has n rows and p columns, and p is bigger than n, so it has more columns than rows. But that means that A can't have a pivot in every column. Remember that when we row reduce a matrix, we think about the structure of the columns and the rows, and we want to try to get one pivot in each of our columns. But we can't do that because each pivot has to be in its own row. So we would run out of rows before we run out of columns. And so that means we have to have a free variable. Ax equals 0 therefore has non-trivial solutions, and that means that our set is linearly dependent. In fact, anytime you have a set of vectors where there are more vectors than the number of entries in those vectors, the set will be linearly dependent. So if you had 7 vectors in R4, I don't care what those vectors are, they have to be linearly dependent. If you had 3 vectors in R2, they must be linearly dependent. But the converse is not true. If you had, say, 3 vectors in R5, maybe it's linearly dependent, maybe it's linearly independent. Not sure. So the converse of this statement is not true. But if you have more vectors than the vectors have entries, then the set must be linearly dependent. Here's another easy way to sometimes identify a linearly dependent set. If a set of vectors contains the 0 vector, then that set must be linearly dependent. To see why, what we can do is renumber the vectors in that set so that v1 is the 0 vector. So maybe the 0 vector in this set was in the middle somewhere, maybe it was v17 or something like that. But let's just renumber our vectors so that the very first thing in the set is that 0 vector. Well, now we can think of the linear combination where we have 1 times that first vector plus 0 times everything else. But that's going to equal the 0 vector, because for the first part of that linear combination, we have 1 times the 0 vector, which will be the 0 vector. And for every other piece of that linear combination, we have 0 times some vector, and that will also be the 0 vector. So that linear combination that you see here is just a bunch of 0 vectors all added together, and that will equal the 0 vector. But it's a non-trivial linear combination. Not all of the coefficients are 0, and that means that our set of vectors is linearly dependent. So here's the process that we go through to determine if a set of vectors is linearly independent. First, we see if we can use either of these quick tricks that we just talked about. Does the set have more vectors than the number of entries in the vectors? If so, then the set is linearly dependent. Does the set contain the 0 vector? If so, then the set is linearly dependent. If not, then we have to work a little harder. If not, what we do is we solve the homogeneous matrix equation, Ax equals 0, where A is the matrix whose columns are the vectors in our set. And what we're looking for is whether or not that matrix equation has non-trivial solutions, or if it has only the trivial solution. If the equation has non-trivial solutions, then the set is linearly dependent. If the equation has only the trivial solution, then the set is linearly independent.